of mankind. It implies that specifically. No dwelling place, for Mercury or Venus or Mars or any of those places. Okay? All right. God says, let the earth bring forth what? Tender grass and the herb and sowing seed and fruit trees, whose seed is in itself, making fruit after its kind on the earth, and it was so. So all the vegetation now is being completed what? End of the third day. All right? The earth was bringing forth tender grass, herbs, sowing seed after its kind, etc., whose seed is in itself, and God sees that it's good. And then there's evening, there's morning, and there you have the third day. And then the fourth day is when he goes into the celestial bodies, and the sun and the moon and the stars, okay? Very, very different from evolution. Okay, now, let's talk a little bit about this water. I'm going to give you a little basic chemistry course here. We can probably break about 8 o'clock, I guess, for a little while. Is that what you'd like to do? Okay. I'm game. You want to sell some books and all. So, not my books. All my books were destroyed in the flood. But the chemistry of water here. Well, water is a substance, of course, that is composed of two elements. Most people know this much chemistry, H2O. At least they know that, right? Not fruit 2O, as you hear in the commercials. Whatever that means. H2O. And meaning representation of two elements, hydrogen and oxygen, in a ratio of 2 to 1. Okay? This is a kind of a picture, diagrammatically, of a, come on, cursor. Come on up. There you go. I knew you could do it. This is a water molecule. The red one is the oxygen atom in the middle, and the gray ones are the hydrogen atoms. And they're joining together by electrons that are being coupled. That's how chemical bonding takes place, okay? And that makes the water molecule a stable entity. It also has some charges on it, although it's overall neutral. It has a distribution of positive charges at the hydrogen, an equal negative charge at the oxygen, but that charge is important because it allows the molecules of water to interact with each other and create these long chains. So liquid water is long chains of water molecules, see? And ice rearranges those chains into unique structures. So it's very important for that property of the water molecule. 2 hydrogens, 1 oxygen, okay? If you give enough energy to the hydrogen-oxygen bonds, you can break them. So you can separate the hydrogens from the oxygen. It doesn't take a whole lot, a couple of electron volts. And they'll break, and they will release these atoms, okay? Now the atoms are more reactive, of course, and they are going to be available for further reaction. But at very high energy, I'm talking about like nuclear fusion energy conditions, millions of electron volts, these atoms will fuse together and form other atoms. Now that's the key. Forming other atoms from the hydrogen and the oxygen atoms that were already in the water. God's chemistry doesn't start with particles. God's chemistry starts with molecules of water, and water in the bulk, evidently. Okay, bulk liquid water. Then he creates, apparently, as far as I can read into this, at least it works out. My research associate and I have been working on this for over 2 years. And as you will see, we worked out the origin of all the chemical elements in the whole periodic table using this approach. So it works on scientific grounds. So I'm satisfied, and I know God's word seems to imply that that's the way it had to happen. So here's the key thing. High energy, free atoms will fuse together to form other atoms, starting with hydrogen and oxygen. So that's where we're going from. Now, a little bit of atomic chemistry here, okay? An atom, the smallest particle that comprises matter, which determines the specific composition of that matter, of course, and the properties of it. So that's the atomic theory of matter. Everybody who had a little chemistry remember that, maybe. If we want to break it down a little more rigorously into its basic particles, we have 3 types of particles that make up the atom: the proton, the neutron, the electron. Well, the proton and the neutron particles are in the center, called the nucleus. That's what this is referring to, right here. And the charged electron particles are out. And there's a lot of space, relatively speaking, between where those electrons are and where that nucleus is. So all those protons are congested with those neutrons tightly compacted into a dense nucleus, and there's a lot of space where these electrons are moving around, kind of like planets orbiting the sun, you know, very much similar idea. So each proton has a positive charge of 1, relative charge of 1. It contributes to the mass of the nucleus. The electrons have a negative charge, but they're so light, almost 2,000 times lighter, that they virtually don't contribute much at all. I mean, literally they do, but not to any measurable extent. And then thirdly, the neutrons are 0. That's why they're called neutrons. They're neutral, no charge. They contribute also to the mass. So it's the nucleus with these protons and neutrons that makes up the mass, okay? So you got positive protons, neutral neutrons, and negative electrons. So you have equal numbers of positive and negative. What do you get? Neutral, okay? That makes the substance stable, because charged matter is not stable independently. So atoms have to be neutral. Going a little further, I don't want to go too far with this because this is quark theory. They're called up and down quarks depending upon what they call the charm of the color of symmetry of quarks. I don't even quite understand all the quark stuff myself. It's quirky. But you got up and down quarks. And up and down quarks determine what kind of particles you're supposed to get. Except for the electron, it seems to be independent. But that's giving you a little more detail on the dimension scale. We're talking about real small sizes, 10 to the minus 18 meters, you know. That's quite small. Sizes of neutrons and protons, 10 to the minus 15 meters. And the atom itself, when you count the electrons outside and all, is about 10 to the minus 10 meters, okay? So these are very small dimensions for a lot of particles to be crowded together. So you've got a tremendous amount of energy inside that nucleus, right? Okay, here's the nature of atoms. The atomic number of an atom is the number of protons. Every element has its own atomic number for its atoms, okay? Tells you what kind of atom it is. Then we have the mass of the atom is called the atomic mass. That's the numbers of the protons and the neutrons that add up to give the mass, okay? And then we have, there we are. We have the term isotopes. Well, isotopes are atoms of the same kind that have different masses. In other words, according to this, they have the same atomic numbers, but what? Different neutrons. That's how they get different masses, okay? So, you know, you talk about hydrogen mass 1, hydrogen mass 2, uranium mass 235, uranium mass 238, and so on. That simply means different numbers of neutrons in the structures of those atoms. And every atom has isotopes, okay? Atomic stability is a relative term. It relates to the free atom being brought into the most stable state when it has no electrical charge. In other words, neutral condition here, all right? So that's why when you say if charged particles came together to form some other particles, they would stabilize by attraction of positive and negative, or they can stabilize another way by electrons interacting with each other. I'm not going to go in all that, but that's chemistry. Okay, here's some examples of isotopes in the periodic table. I only took a few that are pertinent here. If you look at the first group up here, the hydrogen, you'll see 3 types of hydrogen. Come on, Carissa.